Hello, today we're going to talk about structure 2.1.3, and this is all about the structure and properties of ionic compounds. So I just want to remind you that ionic compounds form typically from a metal and a nonmetal because the metal is going to be losing an electron to form a positive charge, and then the nonmetal, I'll use N for nonmetal, is going to gain the electron or electrons to form a negative charge. And then the opposite charges will attract each other. We call that electrostatic attractions, and that forms the ionic bond. But more importantly for this particular section is that they form this lattice structure. So you'll see that the ions are going to interact with each other in such a way that it could be interacting with any of a number of other ions. So I will draw it out like this, but so you'll have positive and negative ions in a lattice, so in a repeating structure, where they could be interacting with a number of different ions. So like maybe this negative one is interacting with this positive one, or maybe it's interacting with this positive one or one of the other ones. You're not really able to tell, and in reality it's going to interact with all of them. So what we do is we use something called a formula unit. Ionic compounds are always counted in formula units, where it's a ratio of the number of positive ions to negative ions. So I drew this one so that it's a 1-to-1 ratio, so something like sodium chloride would be 1-to-1, but not all ionic compounds are going to follow that ratio. You might have something like calcium chloride, where there will be 2 chlorine ions for every 1 calcium ion. And so they do form different structures based on that. You don't need to know specific structures that way. And you should also know that this is happening in 3 dimensions. It's just difficult for me to draw that. So they're interacting in this 3D lattice structure. Those positive and negative charges are attracting each other. And in that way, we need to count the ratio of the ions instead of individual discrete molecules like we would with covalent compounds. Okay, so we talked about that lattice structure. We can measure something then called the lattice energy. If you have your ionic compound as a solid, we can measure the amount of energy that it takes to break apart those atoms into their individual ions as gaseous ions. And this is just to standardize the type of measurement, is by starting as a solid and going to a gas. And then we call the amount of heat that takes, the enthalpy that takes, the lattice energy or lattice enthalpy. And because it is breaking a bond, these are positive values, because it requires you to put in energy in order to split them apart. And it is influenced by 2 main factors: the quantity of the charge, I'll say size of the charge. And so that means something like comparing sodium ions versus magnesium ions. Magnesium ions have a larger charge, so it's going to take more energy to break it apart. The other thing will be the radius of the ion. So that would be the difference between like a lithium ion and a sodium ion. Lithium ions are smaller than sodium ions. They have fewer energy levels. Because they're smaller, they can get physically closer to the negative ion, whatever it is. And that distance makes it more difficult to split it apart. The further away they are from each other, the easier it is to split it apart. And this all comes back down to what we call Coulomb's law. So those 2 things, the smaller the radius and the larger the quantity of charge, the stronger the force of attraction. And so the higher the lattice energy. Okay, so that lattice structure and the strong Coulombic attractions between the ions causes ionic compounds to have certain properties. They tend to have very high melting points and boiling points, because it's going to take energy to split those ions apart from each other. they're also going to have relatively low volatility. Remember, volatility, I can spell. Volatility is how much it is able to evaporate at a given temperature. So you're not going to see very much evaporation at a particular temperature for ionic compounds unless you're past the melting point and boiling point. They also tend to be soluble in water, not perfectly soluble in water. So there's the solubility rules. So some ionic compounds are going to be more soluble than others. But as a general rule, we say that ionic compounds tend to be soluble. And that's because your water molecule is polar and has partial negative and partial positive charges. Those negatives and positives can interact with the negative ions or positive ions in something called an ion-dipole interaction, which causes it to split apart from its lattice structure and dissolve, be able to dissociate. And so because of that, they tend to conduct electricity in water as well. Because you can have those charges that are free to move throughout the solution, and they can conduct an electric charge. As a result of that, they are not very soluble in nonpolar solvents. So you can imagine that electronegativity has a significant effect on the properties for ionic compounds, because electronegativity refers to how much the atom is pulling on the electrons in a bond. So if you have an ionic bond, like sodium chloride, the sodium does not pull on the electrons very much, and the chlorine does. The chlorine is much more electronegative. And so the electrons were going to wind up almost entirely by the chlorine and not very much by the sodium. And so that really large difference in electronegativity between the two helps us to define that as an ionic bond. So really, the greater the difference in electronegativity, the more ionic in character that bond is. Now, fortunately, in section 17 in your data booklet, you're going to have what's called the bonding triangle, and that very clearly defines ionic versus covalent. And it also gets into differences between polar covalent and metallic bonding. But effectively, it's based off of two things: the difference in electronegativity and the average electronegativity. And both of those things are going to make up what we call the bonding triangle. Metallic is kind of over in the corner here. You've got some covalent here, and ionic up here in the top. The electronegativity values are also given in section 9 of your periodic table. So you're always able to look at the specific electronegativity values for all of the atoms, and you can always reference the bonding triangle. However, it's in general, the greater the difference in electronegativity, the more ionic in character that bond is going to be. The closer in value, the more covalent it will be. And so that can also help you decide which one is going to behave more like an ionic compound versus more like a covalent compound. Okay, so let's look at this example. It says element A is in group 2 of the periodic table. That means it has 2 valence electrons, and it's likely to form a positive 2 charge because it's going to lose the 2 valence electrons when it forms an ion. Element D is in group 17, which means it's a halogen. It has 7 valence electrons. It's going to gain 1 when it forms an ion. And so these 2 charges don't balance each other out perfectly. You need to have 2 of the D ions to balance out 1 of the A ions. So the formula, or the formula unit for this ionic compound, is AD2. Now, this is very likely to be soluble in water, because of that, the compound, when it is dissolved in water, is going to separate back into those separate ions, and those ions allow the solution to conduct electricity. However, as a solid, if it's completely stuck in that lattice structure, and it's not going to be able to conduct electricity when it's stuck in that solid. So this section also links to some of our experimental techniques. So what kind of data demonstrates the physical properties of ionic compounds? We can measure things like conductivity as a solid, and conductivity in solution. We can also measure things like melting point and boiling point. And we can also test things like solubility in water or in nonpolar solvents. Okay, and then so how can lattice energies or lattice enthalpies and the bonding continuum, so that bonding triangle that we talked about from ionic to covalent bonding, explain the trend in melting points of the metal chlorides across period 3. So the period 3 chlorides are things, so like sodium chloride, and then as you go across, it's magnesium chloride, aluminum chloride, and then you get into silicon tetrachloride, phosphorus trichloride, sulfur dichloride, or just Cl2, diatomic chlorine. So this is across period 3. This one is going to be the most ionic in character because there's the greatest difference. And as you go across, right, this one's also going to be very ionic. This one is going to be middling, and then all of these are going to be very covalent in character. And as a result, you're going to see that this one will have the greatest melting point. And then this was 97, 463, 203, like it keeps decreasing as you go across. And that's because you have a very large difference in electronegativity. So the chlorine is going to be more pulling on those electrons more, versus the sodium is not going to have very many. And that those opposite charges will cause it to form those strong Coulombic attractions or electrostatic attractions. On the other side of the spectrum here, you're going to see more covalent character. They're going to be sharing their electrons instead of having this uneven interaction. And that makes it have lower melting points. They're just going to be held together by intermolecular forces, and they're not going to be conductive in water.